Thanks. I'm very honored to talk to you today and to be here with representatives of the ministry and presidency. I wanted to start by asking you a question. I wonder how many people here believe that they were born to be mathematicians? I've got one at the back. You know, that you could have gone on and made discoveries in mathematics if you'd chosen to. So I only have one hand up. A couple, good. How many people sometimes found math a little difficult or mysterious, or you struggled sometimes? So I'm actually in that group. Thank you. When I was young, I didn't think I had mathematical ability. I'm a mathematician now and a playwright, but I didn't think I had ability in either area. And when I was growing up, I would always compare myself to the kids who wrote competitions, who seemed to get math without any effort. And I became quite convinced that I couldn't do it. And my fears were confirmed when I took calculus the first time at university. I don't know how many people have taken calculus, but I was basically saved by the bell curve. I failed, but the bell curve brought me up to a C, which I was very relieved. And even though I'm a playwright now, I also got the lowest mark in my creative writing class. So I didn't think there was too much I could do. So today I'm going to talk about some ideas that developed through my own struggles. And I think this experience that I've had has very big implications for our society, of struggling and then gradually seeing that I could do something. I think that every society is confronted with invisible problems that are very difficult to solve because no one can see them. So to give you a very ancient example, the ancient Greeks were a very progressive civilization. They had breakthrough after breakthrough in science. They established the first democracies. But at that time, even the most enlightened thinkers felt that women were inferior to men, and that slavery was as good for slaves as it was for the slave owners. So Aristotle wrote that some people are born to be masters and other people are born to be living tools. So even though the Greeks were very progressive, they couldn't understand the problems that came from not having an equitable society. And I'm going to argue today that every Western society, every society on the planet, is also affected by a similar invisible problem that has to do with equality. And it's a problem that no one can see, and I think we struggle to develop sustainable economies, to end violence, to develop populations that are happy and fulfilled. I think we struggle in these areas because we have not dealt with this invisible problem. So which way do I point this?
Can you change the slide, please? Yeah, just press here.
Okay.
Maybe those.
So the things I'm going to talk about today are based on some very solid evidence. The Jump Math program, which is a charity that I started in my apartment as a tutoring club about 15 years ago. I just wanted to help some local kids by tutoring them. I had no idea Jump would grow into what it is. But we're very interested in evidence and data, in scientific evidence and data. And I think for too long, teachers have been told to do things that are not based on data. So I'm very proud that we're involved in a number of studies with very distinguished cognitive scientists and educational researchers. And I'll be telling you a little bit about the data we've seen. This is a small list of some of the cognitive scientists and researchers that we're working with across North America, ranging from pilots in Harlem and the Bronx in New York to a very large randomized controlled study that was supported by the U.S. Department of Education in Canada. And I'll tell you about some of these results. So could you change? Thank you. JUMP has been recognized in a number of publications, Scientific American Mind, and I was invited to give a keynote at the Aspen Brain Forum on some of these results. So if you wouldn't mind changing the slide. I'm going to start, though, with a case study to try and illustrate what I mean by this invisible problem. So if you wouldn't mind clicking that. A teacher, her name was Mary Jane Moreau, tested her kids coming into grade 5, and this red curve shows the distribution of marks. The average mark was in the 54th percentile, the lowest mark was in the 9th percentile, and the highest mark was in the 75th percentile. So that's a very typical distribution. That would represent about a 3 grade level difference between the top students and the bottom students as early as grade 5. Now, I've visited hundreds of schools and taught in hundreds of classrooms, and this distribution is universal. I've visited 3 continents and hundreds of schools, and thank you. Is that working now? Okay. So that kind of range is universal, and I'm sure you see it in Bulgarian schools. In fact, this is a private school where parents are paying money to produce this difference. So you can see that as a society, we've accepted these things as natural. No one's complaining, no one's removing their children from the schools. Now, Ontario, where I come from, does very well on the PISA, the international tests. We score quite high. But last year, only 54% of children in Ontario in grade 6 met provincial standards. Only 54% basically passed in grade 6, even though we're a very strong country. Now, I know that Bulgaria produces extremely strong mathematicians, particularly on math competitions. And I'm also honored to be speaking on a day when there's a representative from Finland, which is renowned, its educational system is renowned. But in every country on the planet, if you look closely at the PISA data, for instance, you'll see that there's still a large part of the population that's struggling and is not very good at math, and certainly does not love mathematics. This is really universal, and these distributions are universal. So this is the invisible problem I want to address. The fact that we can't see this as a problem. The fact that we accept year after year a system, not just here but North America and everywhere, that produces these distributions and these differences between children. The fact that we can't imagine as a society that all children, or virtually all children, could enjoy mathematics and love the subject and do well at the subject. So the question is, are these distributions natural? And we've seen a lot of evidence in JUMP that they are not, that they're a social creation. So the teacher, Mary Jane, used the JUMP math program. And I want to say that this is much more important than JUMP. JUMP is one attempt to solve this problem. We think it's well based on some principles from cognitive science on how kids learn. But whether or not you believe in JUMP, we've seen evidence that children have far more potential than we believe. So the teacher followed the JUMP program, the online teacher's guides, for a year, and she retested her children at the beginning of grade 6, and this is what the distribution looked like. So the children on average were in the 98th percentile, and the lowest mark was in the 95th percentile. A year later, the teacher taught her kids for another year, and at the end, a year later they wrote the Pythagoras math competition, all of the children, and 14 of the 17 got awards of distinction, and the other 3 came close. So it was a very different looking class. And grade 5 is very late to intervene. You could imagine if kids were given a great foundation in mathematics right from kindergarten, what they would look like. This class looked like a gifted class after 2 years. You could imagine what kids would look like if they started from kindergarten. Now we've seen, this is a private school, so the teacher had great advantages, but before using JUMP, they had never seen results like this. And we've seen similar results in very different settings. So I was invited to go to Brixton in London, England, to give a demonstration lesson. And when I arrived at the school, I was watching the children at recess playing, and the children would form rings around each other and goad each other on to fight. There were at least 10 fights happening on the playground. The monitors couldn't control the kids, and they had to remove kids from the playground from their injuries. It was the most violent school I'd ever been in. And I didn't know, but they had put a behavioral class together of kids who were really troublesome, kids who were violent or difficult. They put a grade 5-6 class together for me to teach. So I decided I would try and teach the kids about binary codes. Computers only read codes written in zeros and ones. And the children went crazy. They thought they were little code breakers. They wanted longer and longer codes. And at the end of the lesson, I did a mind reading trick that's connected to the binary codes. And all the kids wanted to come up to the front of the class and do the trick. And on the third class like that, when we came in, the kids cheered. They were so happy to be doing all this difficult work. These were kids who were considered to be unteachable. They were so happy to be doing all this advanced-looking work that was connected to computers and science that they cheered on the third lesson. So in Brixton, we were able to work with 1,000 of the most challenged children for 4 years in a row. And in one grade 5 cohort, only about 12% of kids were at grade level, and they expected those kids to fall behind too because they were very difficult students. And within 2 years, 60% had caught up and passed the national exams, with similar results for kids in the program 1 year. So they were able to reproduce these results 4 years in a row, where they took the most difficult and challenged children on the board and got that many to pass the exams. And the most rigorous evidence we have is from a randomized controlled trial that was a real gold standard in experimental design. Teachers were assigned programs at random, and they found that in the jump classrooms, the rate of growth in mathematics was twice the rate of that in the control classrooms. So the jump students progressed at about twice the rate of the control. Now, as I said, this is much more important than jump. I'm going to give you a bit of an idea of why jump works, why we think it works, but what I'm talking about today is the potential of children. Whatever solutions you arrive at in Bulgaria, or whatever initiatives you bring in, you have to keep in mind that this should be the end goal, that far more children than we expect have ability in mathematics. So the question is, why aren't we seeing this? Across the world, why do we see such wide distributions? And that's a very complex question that I want to address today. So one reason has to do with debates in education about how to teach kids. In North America and Europe, there's been a lot of very heated debate about whether to teach kids by more traditional methods, which would involve teacher-directed, lots of memorization, following procedures, versus discovery-based, where the children figure things out for themselves. They often deal with rich, complex problems. And in North America, this has been very polarizing, and discovery has pretty much won in North America for years. That's been the dominant method, although not done very well. And people aren't aware, but both methods have drawbacks. In traditional teaching, quite often it can be boring. Sometimes the teacher's just teaching by rote. The kids don't really understand anything. They just memorize things. That's if it's done badly. And in discovery-based learning, cognitive scientists are now finding that there are real disadvantages to pure discovery too. If kids are given problems that are too complex, they suffer from cognitive overload. Their brains just get overwhelmed, and they lose confidence in their ability. They struggle and actually never want to see a problem again as long as they live. So there's a great deal of evidence now that in cognitive science that a mixture called guided discovery, a mixture of the two types, works best. And so that means giving adequate review. Scaffolding lessons, that means breaking them into manageable chunks and allowing kids to succeed at those chunks. Giving enough practice afterwards. A lot of people think that practice is bad. In North America, educators call it drill and kill, as if it's always going to be boring and frustrating. But there's an enormous body of evidence suggesting that the only way kids become experts is through practice. And the instructional challenge is, how do you make practice interesting? It doesn't have to be boring, but it's necessary. Breaking mathematics into small steps, differentiated instruction, and by that we mean just changing things slightly for students, but not differentiating the outcomes, not expecting that kids will have very different outcomes. And the final thing is continuous assessment. Research shows that kids need constant feedback, and the teacher always needs to be checking where the kids are at and what they know before they move on. So JUMP has produced a series of materials that are now being used in Bulgaria thanks to Yavor, who brought the program here. he actually flew Mary Jane, the teacher who produced that shift in the bell curve. He brought her to Bulgaria to train the teacher. She spent 3 days here. And since then, everything that's happened in JUMP has happened through Yavor and his team. It's been very inspiring for us to see what could happen with no work on our part if a group of dedicated individuals takes something on and tries to make changes. So the one thing I want to point out is that these resources, these teacher's guides that you see there, are free online. We're a charity, so you can go to the JUMP Math website and download all of these if you're interested, if you're a teacher or parent. And also there's a website that maybe you'll post, progresivno, where you can find them in Bulgarian. Is that correct? They've been, Yavor has had a team translate the materials into Bulgarian. So this is an example of what a teacher's guide lesson looks like. These are all online. There's instructions for the teachers. Every lesson is a series of Socratic questions or challenges that are taken up right away. There's lots of discussion. It's very dynamic. But the teacher is constantly giving assessments and not moving on. You've seen kids playing video games, how excited they can get. You can give mathematics the same structure. You can raise the bar incrementally in small steps, and kids get more and more excited as you raise the bar. And then at the end of every lesson, there's extension questions that take the ideas a little further and let the kids get very excited about their progress. Now, most people would not believe that math could be used as a tool for social justice or that it could be exciting. But remember, I told you in Brixton, the kids cheered when they were able to succeed. This is something you can't believe unless you see it. I once even broke up a fight in the school by telling the bully that if he didn't apologize, I wouldn't give him his bonus question. And he apologized so he could get his extra work. And that's what those extension questions are. They're extra challenges for kids. The reason we never see this is because we make the challenges and the steps too big. As adults, we think, oh, the kids are going to get bored if we don't give them huge steps. But actually, kids are very different from adults. They love repetition more. They love practice more. I once was in a classroom where I taught the kids how to multiply numbers with lots of zeros. This was a grade 5 class. So, you just count the zeros, 1, 2, 3, 4, and then you multiply the leading numbers. So I hope I did that right. I actually tell my students I'm not a very fast mathematician. I'm very creative, but I'm not fast, so I'm always worried about making a mistake. So at the end of the lesson, this boy came running up. He'd multiplied two 20-digit numbers, two big numbers, and there wasn't even room for the zeros on the page. They were wrapped around in circles. And, to an adult, that would be incredibly boring. We would have no understanding of how that could be exciting. But this boy was jumping out of his skin. He was so excited. Why? I don't know. I guess because he'd proven he could conquer these big numbers. Because he'd proven a pattern goes on forever. He'd been able to investigate this and try it and see what it would look like. This sense of wonder and curiosity that children are exploding with and filled with, we've forgotten as adults, and that's why we have trouble teaching kids. And that's why we think math would be boring if we teach in steps. Kids are dying to see connections, see patterns, and make discoveries, but we prevent them constantly through fear and anxiety. I think Yavor had mentioned that in a Bulgarian pilot of JUMP, that supply teachers could tell the difference between a JUMP class and a regular class after only 4 months, even when math wasn't being taught, because the kids were more cooperative, engaged, and curious. And by the end of the year, observers had trouble telling the difference between special education children and regular students. And occasionally they could see a difference, but the children were happy to stop and help the other kids. There was an ethic of cooperation. Children were competing, but against the problem, not against each other. It was a very different atmosphere. And I've seen this in classroom after classroom, that when you take away the hierarchies, the unnecessary hierarchies, you get very different behavior. And I think this is one of the main reasons I think we see these hierarchies or these differences. It's our belief that they're natural that's causing them. That's the biggest cause. Because as early as kindergarten, there's research that shows that children start comparing themselves and deciding who's smart and who isn't in subjects like mathematics. And as soon as a child decides they're not in the talented group, then their minds stop working efficiently. They stop paying attention, they stop being engaged, they often develop anxieties or behavioral problems. So, you could argue, well, not every child can learn mathematics, so we should be ranking them and comparing them and making some feel superior and some inferior, because they're going to have to get used to that. They're going to learn one day that they don't have ability. But what if almost every child could learn math? Then I don't think we could have devised a better system for making that, for stopping that from happening. Because we're shutting down brains, we're stopping them from working efficiently by ranking kids and making them feel inferior. And people always argue when they hear about jump, yeah, but what about the faster kids? You're going to leave behind the faster kids. I don't know if you remember Mary Jane's graphs, the graphs I showed you, but the faster kids did way better after jump than before. The entire class went further. Also, there's a lot of research. There's a famous psychologist, Carol Dweck, who's become a superstar in North America because she showed some kids have a growth mindset where they believe that their success depends on hard work, perseverance. Other kids have a fixed mindset where they believe that their success depends on having a gift or a natural ability. She did very rigorous experiments that showed the kids with the fixed mindset do worse and worse over time. The ones who think you need a gift. Because they don't like to work very hard. It shows they don't have the gift. And they also, when they encounter difficulties, they can't struggle or persevere. The kids with the growth mindset do better on average. So I don't think that by telling some kids they're gifted or great, we're actually doing them a favor. It's much better for kids to learn that all children can learn through hard work. Then they actually, first of all, they develop a growth mindset. Secondly, they engage in math for the right reason, not just out of competition to be better than other kids, but because they love the subject and because it's interesting and a very useful subject. So the JUMP model, we're hoping that by training a group of mentor teachers, one JUMP staff member or volunteer can support a number of teachers, and we actually have models of this in Canada. At the University of Calgary, we're actually setting up model schools in the Calgary School Board where teachers are getting mentoring from master teachers. 50 mentor teachers can support 1,000 other teachers who can directly influence 20,000 students. So it's a very cheap model for intervention. You just need one trainer. Now, I just want to mention one other reason maybe why we think mathematics is difficult. I once met an educator who said, I've got a very good explanation of why a negative number times a negative number is a positive number. I don't know if you remember that. So you may have been tortured by that in school. And I said, what's the reason? And she said, when bad things happen to bad people, it's good. So that's a good way to remember, but it's not a great explanation. And I've found that over and over, like teachers are my heroes. Teachers are my absolute heroes. In Bulgaria, teachers are driving the growth of JUMP. They're volunteering. They're spending extra time. I've seen that the teachers get a bad reputation, but I've seen that the vast majority of teachers are fed up with doing things that aren't productive, that don't work, and being told they have to do things that don't work. So they sometimes get apathetic. And also, teachers will admit that they don't know mathematics for no fault of their own. So they're very happy to be able to learn mathematics. So at the Calgary Teachers Convention, I asked 700 teachers why, if you took a whole number like 7 and divide it by 2/3, why you're allowed to flip and multiply. Why is that true? And someone yelled out, because you get the right answer. So that's true, but I've surveyed thousands of teachers, and they always give me very complicated explanations or no explanation. And usually in our training sessions, I'll ask for someone who's very math-phobic, who's terrified, to help me explain this. So actually, is there someone here who could help me? Maybe in the front row who knows no mathematics? I'm just going to ask you a couple questions. Would you help me? No? Someone? I'm only going to ask you a couple questions. It's very simple, because one of the principles in JUMP is go to the right level. So I'm going to go back to grade 2, grade 3. If I say 6 divided by 2, suppose you've got 6 pieces of chocolate. What does it mean to say divide by 2? Anyone give me an answer? What would you do with those things? Very good, thank you. So you divide them into 2 groups. Now, some of you, if you were in grade 2 or 3, might be panicking at this point because you might have done it differently. I don't know if anyone would have done it differently. Some people would divide it like this. And unfortunately for kids in grade 2 and 3, both of those are right. Division is ambiguous. It depends on the context. This, what does the 2 mean here? It's 2 groups. Here it means groups of size 2. So I found that kids don't even get that taught clearly in grade 2 and 3, which is why when they hit fractions later, so suppose you want to do something like this, they have no clue what that means because they don't even know how to interpret it. So I found that for this, first of all, you could start with a chocolate bar because every kid understands chocolate. Most people think that means give me half the pieces. That's not what it means. Going back to the size model, 6 divided by 2, if you're thinking of the size, that means groups of size 2, you'd be putting 2 pieces together, 2 pieces. This says give me even smaller than 1 piece. Give me only half-size pieces. So really what you're doing is you're dividing it up into pieces that size, very tiny pieces. And you imagine the whole chocolate bar like that. I don't know if someone could predict how many pieces you're going to get if you keep going. Very good. Is that clear? Now if I divided it by thirds, then you'd cut it into even smaller pieces. You'd cut it up into thirds. And I hope you could imagine how many would be in the whole chocolate bar. I hope you see a pattern now. What are you doing with these 2 numbers to get this one? You'll notice you're multiplying. And at this point, this works like magic with children. I'd say, oh my God, I can't even draw this one. Who could do this? And I'd give them 6 over 100, 6 divided by 1 over 100. And even in a grade 5 class, all the hands would be up because they'd want to show off with that. So you can see that you're multiplying. That's why you flip and multiply. It's because the bigger this number, the more pieces you're cutting 1 into. And then you're just multiplying by 6. So I hope I didn't go too fast. I also tell my students that if you don't get something, it's my fault. So if I went too fast, it's because I didn't assess you. I should have given you a test now. And it would be a test you'd actually beg for to write because you'd be able to show off rather than being afraid of. So that's the other element of JUMP, is not only to break things into manageable steps, to raise the bar slowly, and then to assess. And we found that's how Mary Jane was able to get those results, by making all of her kids feel capable right from the beginning. So I want to wrap up now, and I think I can take a few questions. Is that right? But I want to come back to this question of the invisible problem. Imagine if we could see the problem. If we actually, when we looked at children, we saw their potential, their full potential. Imagine what difference it would make to society. So there's some obvious differences. There's new studies that show that mathematics is very important for the economy. So there's very rigorous studies that show that children who do well in math are far more likely to graduate from high school, to go to university, to get good jobs, and even to have good health. There's deep connections between your long-term health and your level of mathematical knowledge. Surprisingly, mathematics is a better predictor of academic success than reading. Your academic achievement for young kids is more important than reading as a predictor of long-term success. The firm McKinsey Corporation published a study that said that deficits in subjects like mathematics impose the equivalent of a permanent national recession on the economy. This is in North America, so it's probably the same here. But I think there are also deeper losses that are harder to see and harder to put a price on. So I think we have trouble developing sustainable economies, understanding the threat to the environment, because we don't have any connection to science or any idea of risk. There was a financial crisis because people had no sense of risk around mortgages. There's also an environmental crisis because we have no sense of risk or no sense of the way small things add up. So we're incapable, especially in North America, of doing anything to stop climate change, for instance. We're finding it very hard. But I think the deepest loss is one that people would really find unbelievable. This is a class of children. They're doing that same binary code lesson I mentioned. And you can see how excited they are and the kind of sense of wonder they have. No one's feeding them pizza or forcing them to stay in. They're just doing pure math, pure numbers. And this, I think, because as adults we struggle with math, we have a lot of trouble believing. You know, you could imagine if our governments put walls around our national parks and said only a few people can come into the national park and see the beauty that's here. We would think kids were stunted if they graduated from high school with no understanding of the visible beauty of the world. But we think it's natural for them to graduate with no understanding of the invisible beauty of the world, that you can only really understand through math and science. The incredible elegance of the universe, the symmetries and connections that are awe-inspiring and transcend the human imagination constantly. I think it's every child's right to develop their full intellectual potential, just as it's their right to develop healthy bodies. And we don't have to wait until we've invented some new technology or developed some kind of superhuman teacher. We have the teachers we need right now. The evidence is there in cognitive science. Whether you believe in JUMP or not, the principles behind JUMP are well established in cognitive science. That kids need scaffolding, feedback, all these things I talked about. The question is, are we willing to act on that evidence? If we are, I think we'll have a very different society within years. If we actually were able to nurture the full potential of children, we would have a society that's unimaginably different in every way, I think. So I'm very honored to have talked to you today, and I'm happy to take some questions. Thank you.